All right, so well, first, thank you very much for the invitation to this interesting and stimulating conference. Um, actually, Shirley sent us several emails suggesting that we don't just speak about our results and we insist on questions. So actually, my talk will be more on questions, and then I will just point, I will have a few pointers towards some of my results, recent results. So what I would like to do today is first telling you why I think there are at least some direction in which statistical physics can really bring something to machine learning, at least in some direction that I like, and on which I'm working. And also, well, at the end, I want to go from machine learning to physics, so I want to show you, I think, a problem in physics, which is a central problem in statistical physics, where machine learning can potentially make the difference in the, say, future 5 years, for example. So I will start first with the topics of, let's say, from statistical physics to machine learning. And well, roughly speaking, there are many problems in machine learning in which you are interested in understanding a certain landscape, which is in general is a high-dimensional function, and the dynamics that takes place in this landscape. And I will be more concrete in the following, but what I want to say is that statistical physicists have worked a lot on high-dimensional rough landscape and the dynamics within those landscape, developing the theory of disorder system in the last 30 years. And so this is, well, I think why it's one of the reasons why I think that actually statistical physics can bring a lot on those questions. So, well, first, let me say what I mean by landscape and what kind of landscape do you find in machine learning. So, for example, in supervised learning, you find, well, in general, there is a function that you want to minimize when you train your network, and which is the loss function. The loss function is a function of W, which is the number of parameters created by the data and the true answer that you want that the network gives you. And typically, the number of parameters is very big, can be millions and more. And this function is, well, it's in very high dimension and can be also very rough. Then another example in which you have a function defined in very high dimension that gives you a high dimensional landscape is different problem in high dimensional statistics. So Lenka described several of them yesterday. So roughly speaking, this is just, well, to give you an example, typically you have a signal, which I denote as X star. This signal is corrupted by noise, gives you a signal with something which is X at. This, and what you get is a function of this signal which is corrupted by noise. And what you want to do is what you want to infer what is the correct signal. And you can do it minimizing, for example, the maximum likelihood between Fx at and Fx. So this, again, if X has a vector or a matrix with a lot of components, this gives rise to a function of X, a function which is in very high dimension, and which is potentially very complicated. And well, in this problem, so there is one part which is the landscape, one part of the problem, and the other part is the dynamics. So in these two problems, well, in the case of supervised learning, well, you know that when to train a deep neural network, so you have the loss landscape, and what you want to do is want to minimize it. And you do it by stochastic gradient descent, or let's say generalized version of stochastic gradient descent. And in the case of high-dimensional statistics, there are many different algorithms that one can use. The one in which that I would like to focus on are algorithms that explore and minimize the landscape. And the most simple example is gradient descent. Of course, you can use also some that are not based on the landscape at all. But what I want to understand today or discuss today is, well, the interplay between the landscape that this problem have and the dynamics that is used, which is a gradient descent on variance to explore and minimize the landscape. So in the following, I would like to first focus on, let's see, some questions, again, at the interplay between landscape and dynamics that arise in high-dimensional statistics and optimization problem, and then I will move to supervised learning. So, well, this is just to give you a picture of what one expects, and sometimes actually can prove, but for the moment, what one expects. So what one expects from the point of view of the landscape, and here I will have, of course, some overlap with Lenka. So if the signal-to-noise ratio is very high, what you expect is that the landscape that you have to minimize is simple, has one minimum, and in this minimum, so the X, which corresponds to this minimum, is in the direction of the signal. So this is when the problem is easy to solve. Then if the signal-to-noise ratio goes down, well, typically you expect that you start to have spurious minima in your landscape, But still, there is one particular global minimum here, which again is related to the signal. It's correlated to the signal. And then again, if you if you decrease even more the signal to noise ratio, while you have a landscape which is full of spurious minima, and while you have lost completely any indication on the signal. Now, as again Lenka also insists, it's nice that there is one thing which is important, and again for physicists, is that since you have a high dimensional problem, when d go to infinity, you don't have smooth crossover from one case to the other, but actually typically you have phase transition. So you really expect that the landscape is simple until a certain point, and then it becomes full of minima, but this is a real phase transition that happens to a certain value of the signal to noise ratio. And well, if you ask then when the system is able to find the signal, again, just what you expect is that if the signal to noise ratio is very small, it will be impossible. Then at a certain point it will be hard. So compared to what Lenka said yesterday, now hard, I mean hard for a given set of algorithms. In particular, if I focus on gradient descent, I mean hard for gradient descent. Meaning gradient descent is not able to find a minimum on a time scale which is polynomial in the number of degrees of freedom, even though clearly the signal is there because the global minimum of the energy landscape is correlated to the signal. And then there is a regime in which the signal to noise ratio is so high that the system, finding the signal becomes easy. It can be done in polynomial time. So this is roughly what you can expect. And one of the questions is, can you really show that this is the case in a given problem? Can you compute all the different values at which this phase transition in the landscape and the dynamics takes place? So the typical questions that are asked in this context are, for example, when are spurious local minima bad and when they are innocuous? And this actually is something, again, in which high dimensionality is very important. If you are in low dimensionality, if you have, let's say, spurious minima, you'll say that you are in a case like this. You have spurious minima and you have a good one. But if you start from a random initial condition, well, a certain fraction of the time, you will end up in spurious minima. So the system will not be able, as soon as you have spurious minima, the system will not be able to recover the signal with a finite probability. When take the dimension which go to infinity, this is no more the case. This is a nice one. Even though there are many well, their basis of attraction can be small with respect to a random. There, they can be tapping for the dynamics. So, well, this is a question, and this meaning that I expect in general that the easy phase for the algorithm it's inside this region. So where you have. So then the other question is, okay, if I know everything about the landscape, what can I tell about the dynamics? So the idea is that, well, imagine that I can compute everything, or I can ask God and he can give me any possible answer on the landscape. Since the dynamics is the algorithm that I consider is an exploration of this landscape, what are the properties of the landscape which are very important for the dynamics? In particular, what are the properties of the landscape that allow me to compute this threshold? And in general, well, another question is how can one analyze actually the dynamics? What are the methods and the frameworks, and how one can compute this algorithmic threshold in this kind of problems? And even more, I think, interesting is if I know the property of the landscape, how I can devise actually and invent new and better algorithms. So these are the kind of questions, and what I would like to stress today is that I think that we have methods now and ideas to really make progress on those questions. So, well, so let me tell you first about the landscape. So I gave you a pictorial representation of this landscape, but can one do quantitative computation? And the answer is yes. So thanks to a method actually that was pioneered in the spin glass theory, but has been really put on a firm basis in recent years, first in mathematical physics by Jan Fyodorov, and then more recently by Benarusso, Finger, Cerny, and collaborators on a rigorous way, and on which actually that we also developed recently with Valentina Ross, Gerard Benarusso, and Chiara Camarota. So this method is called the Katz-Rice method, and roughly what it does is that it transforms a problem of finding geometrical properties of random high-dimensional function in a random matrix theory problem. And for the moment, it has been applied to random high-dimensional Gaussian function, but actually we are developing it in order to be able to apply it also to many different other kind of function, non-Gaussian ones, that you recover in the problem of high-dimensional statistics. So this is really a method that allows you to find and to analyze this transition here, and also to compute really the geometric property of the landscape. How many minima do you have? How many saddles? What are the Hessian around the typical saddles, for example? And so, well, this is the part on landscape, and then about the dynamics, so how you can study dynamics in this high-dimensional non-convex landscape. And this, again, is something that was pioneered in the spin glass physics. It started with the work of Simpolinski and Zispelius in 82, but then there have been really a lot of works. And again, it has been put to a certain extent on a rigorous basis by Benarus and Guillaumet in 97. And so roughly what we can do with this method is, again, studying the dynamics, so like, for example, gradient descent in a random high-dimensional Gaussian landscape, or also a random high-dimensional landscape which are not Gaussian, by transforming this problem in something which is a self-consistent stochastic process, which is really, well, it's for people that are used to mean field theory in physics, is really dynamical mean field theory, actually, of the very same kind that is studied a lot here at the Flatiron for quantum physics. And so thanks to this method, we can analyze the dynamics, and we can, at least for the moment, in simple case, we can study where, for example, where is the algorithmic transition are. And so what we did it recently, I think, I mean, for the future, one very important direction, interesting and promising direction, is combining these two methods and the concepts that go with them, so with landscape and dynamics, to treat several problems in high-dimensional statistics. And well, as a first, we did the first, I think, successful work on this together with Lenka, Florent, and Chiara Camarota, Pierfrancesco Urbani, and Stefano Sarao on matrix tensor PCA, in which really we can really combine the two and I think have a complete qualitative and quantitative solution. But I think it can be much more than that. And I think Florent will talk about this. So I won't tell you more about this. So, well, this is for dynamics and landscapes in high-dimensional statistics, in which I think there is a very interesting thing to do in the future. And now I would like to go on supervised learning and deep neural networks, where, again, I think this perspective based on dynamics and landscape can be interesting. So let me, well, this just make a brief introduction to the problem. It has, of course, an important overlap with what Nati said yesterday. So in the case of supervised learning and deep neural network, of course, you have a landscape, which is the training loss that you want to minimize. But you have a new ingredient in the problem is that you just, I mean, the problem is not just minimizing the training loss. The problem is also finding minima which are able to generalize. And if you want to try to see what are maybe some very interesting questions in the field, well, you can do it looking at result of a numerical simulation, exactly as Nati said. So this is very similar, actually, to what Nati showed yesterday. This is from a paper, but I mean, there are papers before, in particular the Nati's paper of 2015. So what you have here is the test error of 5 hidden layers fully connected network called MINST. It has to classify odd and even number. And what you have, so here is the function of n divided by n star. N is the number of parameter of the network. N star is the value such that if n is larger than n star, you have fit all the training data. So it means that if n is larger than n star, the training loss at the end of the training is 0. And so the continuous curve that you see here are, well, these are different examples. Let's just take one curve. And so what you see, the training curve, so the continuous curve is the test error at the end of the training process. The dashed line here is the minimal test error that you can reach if you do, for example, early stopping. And so what you see in this figure are two effects. The first one, which was highlighted by Nati yesterday, if n is very, very large, what you see is that the test error is going down. So if n is much larger than n star, you're actually over-parameterizing a lot. And so naively, you could think that this would give something which is not good. Well, the answer is no. Actually, the more you over-parameterize, the better it's becoming. Also, the difference actually between the continuous line and the dashed line, which is, let's say, the amount of overfitting, is also. So, well, this, I mean, just an empirical results that has been found also by, of course, by many others. And well, it really raised the questions of, well, why the more you over-parameterize, actually, the better you do. What it seems, at least from these experiments. In general, I mean, the questions which are really important that Nati highlighted yesterday are why actually deep neural networks are able to learn in realistic setting, meaning that with the kind of dynamics, with the kind of initial condition, with the kind of data and architecture that we consider. So I think that many of these central questions can be addressed, at least to a certain extent, using, again, this perspective based on landscape and dynamics. So this, again, this perspective is, I would say, is really orthogonal in a sense to what Stefan discussed yesterday. So you forget completely, in a certain sense, about the data, about the architecture. The data and the architecture are there because they construct the kind of energy function or loss landscape function that you have, but you're not looking really at real data. What are, for example, what are their symmetries and what are their properties? In a certain sense, it's similar to I mean, these two complementary approaches similar to something that has been done also in physics. So in physics, to understand, for example, the behavior of interacting particle in 3 dimensions, there have been different complementary approach, one based on the energy landscape, the other one based really on understanding in real space how particle moves. And really, I think, I mean, at least in physics, the real solution came when the two approach actually worked together, and I mean, one was useful for the other. So, well, what I want to stress is that I think many of the questions that are asked can be asked also from the perspective of landscape and dynamics. And there are several ones which are, I think, very interesting that are on which many people work. In particular, for example, what are the geometrical properties of the loss landscape of realistic deep neural networks? Clearly, there should be something in the property of this loss landscape that is related to the ability of generalize of deep neural network, and also to the fact that with the kind of dynamics that we use, we are able to find minima that generalize. So other questions are, if I change, I go from under-parameterized to over-parameterized, what really does change in the landscape? What characterize good minima that are able to generalize well? And well, I mean, more generally, what are the features of the landscape and dynamics that enable learning? So in this case, I think the way, I mean, it's, and this is my, of course, it's my opinion, is the way I would go. I think the way to go is really to combine numerical experiments with theoretical analysis, something that we do a lot in physics. So from the point of view of numerical experiments, I think there are already many. So there are some that can probe directly the landscape. So they can study, for example, the wideness of the minima, their properties, the barrier between them, and try to connect to generalization. You can also study the dynamics. Something that we did, for example, in this work was to study the dynamics of realistic deep neural networks, measuring observable that are usually measured in statistical physics to check whether a dynamics is glassy or not. And what we show is that, well, for realistic deep neural network, in the over-parameterized regime, the dynamics is not glassy, measuring this correlation function, and is actually in agreement with the fact that the energy landscape has no spurious local minima and is characterized by a big flat manifold at energy 0 for the training loss. And instead, if you go under-parameterized, then the landscape becomes really glassy, and then you don't find actually, then the system, it doesn't work. And then, well, there is also a lot of things that can be done theoretically, and well, first on the rigorous side, and also study, as is done often in physics, mean field and scaling limit. And I think I won't tell you more about this because I think Johan will discuss several results on this. Okay, so this is what I wanted to tell you from, I mean, what I think are the questions and the methods and the ideas that can go from statistical physics to machine learning. And now I want to change gears and actually do the reverse. And now what actually machine learning can bring to a central problem in statistical physics. So, well, a central problem in statistical physics is to understand amorphous solids. So, well, first, I mean, the majority of solids that you encounter in life are not the order crystal that maybe you studied university, but actually what you are amorphous. And here you have example of amorphous solids, glasses, for example, plastic bottles, granular material. These are microscopically very different, but they are all example of what we call amorphous solids. So they have no long-range periodic order whatsoever. And understanding their property and their formation is still one of the central problems of modern statistical physics. And I think machine learning can be really a new tool in this context. So first, well, to make you understand what the problem is, let me make the difference between order solid and amorphous solid. So, and why order solid are easy and well understood, and why amorphous solids are not. So order solids are like this. So you have particles that are arranged with a well-specific crystal order, a periodic order. We understand their formation. They are formed through a first-order transition from the liquid, which is disorder, to the solid, which is, has periodic order. And then we understand also their mechanical properties very well. Instead, if you look at how a glass, the difference between a liquid and a glass, this is really puzzling. So here you have an example of a simulation of a mixture of particles that form, and here you have a liquid. Here, all the particles will move and the system will flow. And here actually you have the same example, but now it's at a lower temperature. You have a glass. It means that even with the best computer, this is not going to flow on any time scale or on any reasonable time scale. And the thing which is really puzzling is that, well, if I didn't put liquid on the left and the glass on the right, you wouldn't tell the difference between the two. I mean, from the structural point of view, it looks like they are really similar, which is very, very different from what happened to crystal. Here, this is clearly a configuration which is extremely different from the configuration of particle that you have in a liquid. And this is part of the problem. It's not clear, even though dynamically it's clear that a glass is different from a liquid. It does not flow. It's a solid, but it's very, very slow. I mean, from the point of view of physics, microscopically, it's not clear what's going on. And to make you understand, there are two problems that in which machine learning, which are central in which machine learning, I think, can be very useful. First is the mechanical properties of amorphous solids. So again, in the case of crystal, mechanical properties are very well understood. You know that are related to defects on crystal order. So this is the dislocation. It's a defect in the crystal order. And if you shear a crystal, well, what happens is that if you put a stress on the boundary, you try to do this, you put a shear stress. If the shear stress is higher than a certain value, dislocations start to move, and you have plasticity. So it's clear that mechanical properties in order solids are related to defects of the crystal order, which are well known, are dislocation. Now, in the case of the glass, well, again, the structure looks really, really disordered. Here is an example of a very glass. Even if you look microscopically, you cannot see any defect in the sense that, I mean, the system is disordered, so it's not clear a defect to what. And if you shear the system, so here I'm shearing the system. So blue, it means that you have, let's say, irreversible motion. Red would mean that you have irreversible motion. And what you see is that nothing happens. It seems that nothing happens. Then at a certain point, boom, you have a kind of fracture in the half of the sample. Now the question is, well, if I give you this configuration, can you tell me where the fracture is going to happen? If you gave me the same thing for a crystal, I would know. I would just see how dislocations are, etc. In a glass, I don't. And understanding where it is, of course, is important for application, but it's also important to develop a theory, actually, of mechanical properties of amorphous solids. And similarly, another problem which is related, in a sense, to it is in the formation of amorphous solid. So here I don't have a movie, but I can show you. So if I have a liquid and I look at the displacement of particle between time 0 and, let's say, half of the relaxation time, and here what you have vectors which correspond to the displacement of the particle. So again, at the beginning, you would see at equal 0, you would see particles that are arranged in a very disordered way. But then after a certain time, you would see that there are really regions that move and regions that don't. And again, the question is, well, if I give you the initial configuration, I mean, can I predict where are the regions that are going to move? And what there is in the structure that makes that this region move and the other ones don't? So while this, of course, there are theories about it, but they are, let's say, not conclusive. And I think using machine learning could be really a promising tool to make advance. So the idea is that we know how to do now large-scale simulation to produce really a realistic sample of glasses, to study their mechanical properties, to study their dynamics. And what we can try to do is to use a machine learning technique to see if we can predict where the system is going to fail. Because we can produce, for example, many, many different, let's say, sample, meaning that we take a glass, then we shear it, we know where it, so we know the initial configuration and we know where it fades. And we produce a lot of sample like this, a lot of data, and then we try to use machine learning to see whether we are able to predict where it's going to fail. And again, I think it's not just about prediction, even though already being able to predict would be very, very cool. But then the idea is also to use this to try to improve the theories. So so if the prediction is very good, it means that the machine learning technique has found something in the structure that is very relevant. And so we can try to make this in connection with the existing theory of amorphous solids. And so there are already, so this is something that there are projects that are just starting. So they are starting about the theory of plasticity. This is the group of Andrea Liu. And in the theory of formation of amorphous solids, so what are the regions that really are going to move? If I give you the initial structure, this is something that we are doing with the group, also with the group of Andrea Liu. And I think this is really a very promising and potentially important topic of application to machine learning to physics. So thank you for your attention.
And the easier part, and again to explain in the easier part, you in very high dimension you can hope to have bigger valleys to which you'll converge. So I understand that you made an analysis which is independent from the architecture, but suppose 1 second we try to relate it. For example, if you have a very structured architecture like a convolutional network, it has a tendency to converge. If you have a structure such as a multi-layer network with no structure, it has a tendency not to converge and probably to be hard. Is there a hope to relate it?
Yeah, well, so this is exactly what we are doing with Johan a little bit. So so what we do, for example, is we train. So for the moment, is what we are doing is a purely numerical experiment. But the idea is that you can, for example, see if you start with an initial condition with the symmetries of the convolutional network, and then you run the dynamics in the fully connected space, which is equivalent, then you see that this prior that you put in the initial condition helps you a lot. So in a certain sense, it looks like there is a basin which corresponds to convolutional network that you cannot find if you start with the initial condition which correspond to a random fully connected network. But if you put this prior, then you go there. And so in a certain sense, I think from this point of view, the architecture, it gives you some particular basin in which you can go. But the problem is that if you don't put any prior in the initial condition, you will never go there. You will never find this basin.
First, you said, do you see in your work anywhere you can tell like the design or the X, the input to the network get reflected in your different landscape? I mean,
the input, so the structure of the network?
The structure of the, say, ImageNet. If I take a different database, not ImageNet, how would that make things easier or harder for your landscape? Because that has to play a role, right? Even in simple linear regression, if you have a good design, you're going to figure out the slope very easily.
Yes, yeah.
I would think that something like that has to be in play here.
Yeah, yeah. So so of course, yes, indeed. I mean, if you look at the dynamics, I think the more the data are complex, the more indeed it's difficult actually to explore the landscape. You can also play with the number of data. So if you use a small number of data, or you can use also the number of parameters of the network to play with. So the data and the architecture. So if you take, for example, a small number of parameters, then the energy landscape becomes extremely complicated. It's probably, and actually the network performs very badly. And then when you go to over-parameterize, then it performs well. And then I think you can, so there are, let's say, two axes. One is the complexity of the data, and the other one is the number of parameters of the network.
But I thought the number of parameters is not the right complexity measure because they are very dependent. So at least there is this paper by the Stanford group have this peak too, right? When you have the number of parameter larger than, and they have some mathematics. But we did some experiment, like if you just do PCA, then you remove that peak. Because when you go to larger number, it's a very bad estimator.
Mm-hmm.
So how do you have a right measure of complexity for?
From the landscape?
Yeah, because I think the number of parameters is often not the right measure of complexity. So if you have the right measure, you're probably going to remove the peak.
Yeah, I don't know. I mean, that's a good question, but I don't know what would be the measure of complexity based on the landscape. Yeah. So
For like images or videos or.
So, I mean, the idea is that, so maybe we didn't go much in this direction. So the idea is that, of course, we have an a priori, meaning that there are physical theory. I mean, there are theories that have been developed. So we have an idea of, for example, what kind of data we are going to use. So, for example, we're not going to use the particle position, but we are going to use, for example, the correlation function, the, let's say, instantaneous correlation function between particles, because this is what we think from theory that are important. So the idea goes in this sense, is that we have a strong a priori coming from different theories. We will use this a priori to construct the machine learning techniques. And then, well, if you get good prediction, and then this will tell us how much actually our, let's say, I think our theory is good or not. That's the idea, but it's the beginning, and so I can tell you more.
Glasses.
Yeah.
So I think what they did is they linked local structure to short time scale dynamics.
Yeah.
So this kind of softness is what atoms move on a very short time scale, given what structure they have. But my concern is that the glassy behavior is precisely not about short time scales. It's about long time scales. And you can, in an amorphous material, you can observe all sorts of short time scale dynamics that has nothing to do with what the material is going to do on the long time scale. So how do you think this can be connected to?
So I think, well, there are two answers to your question. So the first one is that it's true that they look at short time dynamics, but they look at some very peculiar short time movement. So these are, I can call it them short time irreversible movement. So it's true that they don't have a predicting power, meaning that I start at equals 0, I can predict what are the particles that are going to move in a very distant future irreversibly. But they can tell you when a particle moves irreversibly, well, the reason is that locally, the space, the arrangement is in a certain way. So I think they are halfway, I think. So what I would like to do is really what you said, and this is what we are starting to do in the second. So it means that it's prediction on long time.
Because these amorphous systems are very dissipative, right? So you can imagine the moment you touch them, meaning anything you do, you stress them, all sorts of tiny irreversible rearrangements take place.
Yeah.
And that doesn't yet address the time scale, this peculiar time scale.
Indeed. So what you, in a certain sense, this is just noise that should be filtered out. But there is something, again, this is why also I think it's hopeful to predict, because in a sense, I mean, prediction is easy. You just integrate Newton equation, and then you can predict. But there is a lot of junk actually that you just don't care about. So what you would like to extract using a machine learning technique is what is relevant really to have prediction at long times. And this is what we are doing right now in the second point.
A measure of complexity which defines to relate that measure of complexity from the structure and potentially distribution of data. If you take the approximation point of view, you are also after a measure of complexity, which would be the regularity of the function, which allows you to approximate it with a limited number of terms. So then there is a question, are these two notions of complexity equivalent? And have you thought about that kind of question?
Yes, but I mean, my answer can be completely wrong, but I can tell you, I mean, what I think. I think is that, yeah, if the function is that you want to approximate is very regular, then it means that probably, I mean, the basin, so there is a basin which corresponds to it, which is very, very wide, very large. And then the reason why, I mean, let's say, things work is that first you start with an initial condition, which is, let's say, taking random weights, which already is a function which is very regular. Then you do a dynamics, which is, I mean, it's not, you don't do a very large exploration, as Nati was saying, because you have a finite number of data. So you start from a very regular function. You have a wide basin, which is related to this very regular function, a very regular target function. And then this is why actually you're able to find it. So if this function was not regular, this will be a minimum, which I think would be not wide, would be very like this, and would be extremely difficult to find just by going down. So I mean, my intuition is that the regularity is related probably to the wideness of the basin. The structure is probably, of the network is probably a prior, which brings you in the direction of the wide basin. So that's my idea.